All right. Um, Good evening, everyone. Thanks for joining. Thank you, Ritesh, for joining. We will start today's class. Maybe more people will join now. Um, so this is week six of numerical methods course, and we have 2 more weeks to go. And in week six, if you see what we studied, it's numerical differentiation. I hope I'm audible. Let me check my recordings also. Yeah. So in week six, what we studied is numerical differentiation, and how do we use these interpolation formulas for you know to find a numeric to do numerical differentiation, or to find derivatives, first order or second order derivatives for a point that we for any point within the data points that have been given. So that is what we studied. So we studied different formulas. First thing is Lagrange interpolation, and then we also studied divided difference formula. We also studied all the Newton's forward and backward difference, and what is it, Bessel, Stirling, central difference formulas. How can we use all those to find the to do numerical differentiation, and also method of undetermined coefficients. So that also we studied. So I think in week assignment, week six assignments also includes almost like all of the methods. So today I am going to focus on three problems, and those are going to be Lagrange and Bessel's formula, and also based on there's one more, Newton's forward difference. So we will solve these three problems. I hope that would be helpful. So before we get into problems, we'll quickly go through what are the things that we uh, studied in this week. So in numerical differentiation, first thing we started with is Newton forward interpolating polynomial. So this we already know. In we whenever set of data point is given, we need to construct a polynomial in it. And once you construct, you can construct it based on different ways. One is Newton's forward interpolating polynomial. So once you construct that polynomial, you can differentiate that, and you will be able to get the uh, uh, derivative of that function at any point or in within the range. So that is the main idea behind this. So we use all the interpolating formulas that we studied here. That is what we did here. First thing is Newton's forward interpolating formula. This is our interpolating formula. Now you differentiate it. If you differentiate it, uh, carefully, you will end up having dy by dx to be something like this. Okay, and then again you can differentiate it n number of times. That is going to be equal to the degree of the polynomial. Okay, so you can also do d square y by dx square. You can also find d cube y by dx cube. All those things you can find, provided you have uh, enough set of data points to construct that polynomial. So for example, let's say if you want to find, you need at least 2 points to find dy by dx. You need 3 points to find d square y by dx square at least. So if you have more, it is better. So if you want a nth degree polynomial, you need at least n plus 1 data points at least. And if you have more than n plus 1 data points, it is better. Okay, so that's what we do. But yeah, of course we need to construct the polynomial to that degree, and then you can differentiate that polynomial multiple times to find the derivative. So the same thing we can do for backward difference. Only thing is the polynomial is going to be slightly changed. These coefficients will be slightly different than what you see here. Okay, um, these coefficients we just gave for three terms. It doesn't mean you have to restrict yourself to three terms. You should actually include all the other terms too. Okay, for just to give you an idea, we gave only three terms. Okay, and then the next is Lagrange interpolating polynomial. In Lagrange interpolating, you have Lagrange coefficients. You find the coefficients and substitute in the polynomial. You will end up having the Lagrange polynomial, and you differentiate that polynomial again. So it's the same concept. Okay, and similarly, same thing goes to Newton's divided difference. So I did not write explicit expression here, but you understand the logic, right? And yeah, you can also find maxima and minima. Finding maxima and minima is no big deal. So when we say the function has reached maxima, we are telling that there the derivative is zero. Maxima, either maxima or minima, there the derivative is zero. So now you differentiate it further. So the second order derivative at that point will tell you whether it is a maxima or minima. Okay, so at the end of the day, you can use this numerical differentiation technique to find maxima and minima of a function. Okay, and error of the term also you can, error term also you can differentiate the error term to find the error in the dy by dx or any derivatives. Okay. All right. So similarly, you can also use finite difference operators that we saw to do these calculations. And then we can also use Stirling's and Bessel's formula uh, to do this, to find the numerical, to perform numerical differentiation. And finally, what we saw is method of undetermined coefficients. So in method of undetermined coefficients is nothing but you first define a set of stencil. We call it stencil. Um, uh, so stencil is nothing but, uh, let's say you want to define dy by dx in terms of some data points. Okay, so how many data points that you need to take is the stencil that we talk about. Let's say I want to find dy by dx at y equal to at x equal to x naught. Let's say now there could be number of data points above x naught or below x naught. So what are the data points that you are going to take? And if you take a different set of data points, how your polynomial should vary. So that is the method of undetermined coefficient. So you said, like, let's say you take three data points, one is positive, like one is above and one is below x naught, and now you express each data point in terms of Taylor series. That will be your second step. And then third step is to uh, express the like you need to, let's say you seek for f dash, so you need to write this Taylor series in a different way, and then you substitute the series expansion in this and compare the coefficients a and b, and you get the final uh, polynomial. So for example, if let's say you are using f of x, so let's say I want to find f dash of x naught. Now let's say I'm using f of f at x naught and f at x1, which is a next data point, and f at x3. Let's say I'm not using the second data point, is I'm using the third data point. Let's say I want to use only these three, the x0, x1 and x3. Now if you want to construct a polynomial with it, and if you want to find derivative, you are going to express this derivative as a function of these three function values. Now if you write the Taylor series expansion, and if you substitute the Taylor series expansion in this relation, you can find this 9 minus 8 minus 1 and 6h. Okay, by comparing the coefficients. Similarly, you can also express, if it doesn't matter, it is for equal intervals, you can also express it for unequal intervals. You can, so instead of 1 0 and 3, you can also express it as 1 0 and minus 1. Okay, you can also do that, but when you do that, it is going to be this is probably going to be I think this is going to be 1, this will be minus 2, and this will be 1, and below it will be probably 2h. Okay, so you can see that. So let's say if you use f1, f0 and f of minus 1, if you want to express this as df by dx is some function of f0, f1 and f of minus 1, then probably this is going to be 1 minus 2 1 and 2h. Okay, so probably I'm guessing it. So that is one way you can express this thing, or you can also express it in terms of let's say, for example, uh, so let's say if you want to write f dash of x naught as some function of f of 1 and f of minus 1, so this is going to be f of 1 minus f of minus 1 divided by 2h. Okay, so this is going to be your final answer. I'm just giving you the final answer. Okay, similarly, let's say I want to find f double dash of x, so that you can express, let's say I want to find it in terms of f0, f1 and f of minus 1. So for this is going to be f of 1 minus 2 f naught plus f of minus 1 divided by 2 h square, or maybe h square. Okay, so this is how this varies. Okay, um, so this is an exercise, you can do it by yourself to find out. So but the methodology is this: you just express all these function, all these f of x naught, x1 and f of x minus 1 um, as a Taylor series expansion, revolving around x naught, and you substitute that into the polynomial that you seek for. Okay, so basically what you should substitute is f dash of x is equal to, you're writing it as a times f naught plus b times f of 1 plus c times f of minus 1, and then these are all Taylor, you express it as a Taylor series expansion and then substitute them. Okay, you will get it. All right, for more details you can again always go and look back at the um, you know what is the lectures. Okay, all right, so this is what we saw. The next week, so till now we studied numerical differentiation. Next week is going to be numerical integration. Okay, we will study some formulas like trapezoidal rule, Simpson's rule, to do differentiation. All right, any questions? All right, I'm hoping there is no questions. There are new people, lot of new people joined. Okay, if there are no questions, so what we will do is we will solve three problems. As I said, I have three problems today, and one is on Lagrange interpolation, one is on Newton's forward difference, and the other one is on Bessel's interpolation. Okay. Let's solve the first problem. The first problem is to find the value of f of x. Sorry, the value of f of x at different values of x is given by this table. So x and f of x is given. Now we are asked to find f dash of x at x is equal to 3. So it's somewhere over here. At x is equal to 3. You need to find f dash of x, not f of x. Okay, and we were asked to use Lagrange interpolation formula. Okay, so let's first write down the formula. So basically it's a Lagrange polynomial, right? So we are trying to approximate f of x as a polynomial p of x, where this polynomial is a Lagrange polynomial, which means um, it's nothing but summation of probably n equal to 0 to I don't know, some value. Um, so how many points? So let's check the, what did we use? N. Okay, I used I equal to 0 to n p n of x f of x I. No, not p n of x, it's p I of x. Okay, so this p I of x, sorry, not p I, it's l I. So this l I is the Lagrange coefficient, and f of x I is what you know from the table. So or let's say if I want to express it, so this p of x is going to be so you have so this is your x naught, this is your x1, this is x2, this is x3, and this is x4. So you have like 5 data points. So you're going to have 5 uh, terms in this polynomial, which is going to be L naught of x, f of x naught, plus L1 of x, f of x1, plus L2 of x, f of x2, plus L3 of x, f of x3, plus L4 of x, f of x4. Okay, so now this x, f of x naught, x, f of x1, all these are data points, right? It is a constant. So what we were asked to find is f dash of x, that too at x is equal to point, is it 0.3? No, 3. X is equal to 3. This is where we were asked to find, which means this can be approximated as p dash of x at x is equal to 3. So this is what we need to find. So we need to differentiate this entire polynomial, and you need to substitute x is equal to 3. You will end up getting your f dash of x at x equal to 3. So let's write this down. So p dash of x is going to be, since uh, these f of x naught, x1 are constants, these are from the table, this is only the function of x, so you have to differentiate only the Lagrange coefficients. So let's do that. This is going to be L naught dash of x, f of x naught, plus L1 dash of x, f of x1, plus L2 dash of x, f of x2, plus L3 dash of x, f of x3, plus L4 dash of x, f of x4. Okay. All right. So now we need to find Lagrange coefficients. Let's try to find out Lagrange coefficients. So what is L naught of x? L naught of x is nothing but x minus x1, x minus x2, x minus x3, x minus x4. We have till x4, divided by x naught minus x1, x naught minus x2, x naught minus x3, and x naught minus x4. I think here is where I may need your help. So I might make silly mistakes here, so please be careful. So here we will have to substitute the values. So x1 is 1, 1, 2, 4, 7. So this is going to be x minus 1, x minus 2, x minus 4, x minus 7, divided by x naught is 0. Okay, it made our life easier. So this is going to be 0 minus 1 is minus 1, 0 minus 2 is minus 2, 0 minus 4 is minus 4, and 0 minus 7 is minus 7. So this is nothing but 24887 is 56. So this is going to be 1 divided by 56 into x minus 1, x minus 2, x minus 4, x minus 7. Okay, but we cannot substitute L naught. We need to have L naught dash of x. So which means we need to differentiate this Lagrange coefficients with respect to x. Okay, so let's do it here itself. L naught dash of x is equal to, how do we do it? So 1 by 56 is common. Let's keep it out. So this is a, so these things are in multiplication. So we will apply the UV method, right? So first, let's say you differentiate this and you keep the other things constant. So when you differentiate x minus 1, it's just going to be 1. So in fact, that is true everywhere. If when you differentiate this, it's going to be just 1. Similarly, everywhere it's true. So we can write this as, so when you differentiate x minus 1, it's going to be x minus 2, x minus 4, x minus 7, plus um, similarly, when you differentiate x minus 2, this is going to be x minus 1, x minus 4, x minus 7, plus this is going to be x minus 1, x minus 2, x minus 2, and x minus 7, plus x minus 1, x minus 2, x minus 4. Okay. Now, what we actually need is p dash of x at x equal to 3. So let's substitute here also. Let's find out what is L naught dash of x at x equal to 3. You can you can subs you, I mean, you can assemble everything and substitute, but here it's easier to substitute it here. So this will be 1 by 56. What will happen if you substitute 3 here? The first term will be 3 minus 2 is 1. You guys can also do it parallelly and let me know what is the final answer for L naught dash of x. Okay, so 3 minus 2 is 1, 3 minus 4 is minus 1, 3 minus 7 is minus 4, plus 3 minus 1 is 2, 3 minus 4 is minus 1, 3 minus 7 is minus 4. Then this is going to be 2 1 minus 4, and this is going to be 2 1 minus 1, correct? Yeah, and so this you can write it as 1 by 56. This is 4, this is 8, then minus 8, and then minus 2. So this is nothing but 2 by 56, which you can write it as 1 by 23. Okay, this is your L naught dash of x. Now let's similarly you need to do for all the other remaining Lagrange coefficients. L1 of x. So L1 of x, again you can write it as x minus x naught, x minus x2, x minus x3, x minus x4 divided by x1 minus x naught, x1 minus x2, x1 minus x3, and x1 minus x4. We can also substitute it here. X naught is 0, so it's going to be simply the same. So it's going to be x times x minus x2 is, I guess, 2. Yeah, x2 is 2, x3 is 4, and x4 is 7, divided by x naught is 0, so this is going to be simply 1, and 1 minus 2 is minus 1, 1 minus 4 is minus 3, and 1 minus 7 is minus 6. So this is nothing but it's going to be negative minus 1 by 18, I guess, minus 1 by 18 into x, x minus 2, x minus 4, x minus 7, correct? So now you want to find L1 dash of x, so let's differentiate this. This is minus 1 by 18 into x minus 2, x minus 4, x minus 7, plus x, x minus 4, x minus 7, plus x, x minus 2, x minus 7, plus x, x minus 2, x minus 4. Okay, now let's substitute x to be equal to 3. Okay, now when we substitute it, what will happen? 1 by 18. If you substitute 3, 3 minus 2 is 1, 3 minus 4 is minus 1, 3 minus 7 is minus 4, and here it's going to be 3 and 1 and minus 4, and this is going to be 3, 1 minus 4. It cannot repeat, right? So this has to be, okay, this has to be minus 1, sorry, minus 1, minus 4, and this is 3, 1, minus 4, plus this is 3, 1, -1. All right, now let's if you simplify this, -1 by 18, this is going to be positive 4, this is also going to be positive 12, this is going to be -12, and this is going to be -3, correct? Yeah, so these goes away, so this is going to be simply 4 minus 3 is 1, so it's going to be simply -1 by 8. This is your L1 coefficients. Now we need to do the same thing for the other three. Let's do it. L2 of x, which is going to be x minus x naught, x minus x1, x minus x3, x minus x4, divided by x2 minus x naught, x2 minus x1, x2 minus x3, x2 minus x4. So if you substitute it, x naught is again 0, so x into x minus 1, x minus 4, x minus 7, divided by, you will have 2, x2 is, I guess it's 2, x2 is 2, yeah, so x2 is 2, 2 minus 0 is 2, 2 minus 1 is 1, and 2 minus 4 is -2, and 2 minus 7 is -5. So this can be written as 5 to is 10, 10 to is 20. So there is no positive. So this is 1 by 20. Okay, correct? Yeah, 1 by 20 into x, x minus 1, x minus 4, x minus 7. Now, what should we do? We should differentiate it. L2 dash of x. This is going to be 1 by 20. Similarly, when you differentiate with respect to x, the first term, the other terms remain same, so we can write it as x minus 1, x minus 4, and x minus 7. Now you keep the x and you differentiate with respect to x minus 1, so this is going to be x minus 1, x minus 7, plus x, x minus 1, x minus 7, plus x, x minus 1, x minus 4. Okay, this is simple mathematics, so I'm just going fast. So if you guys have any doubts in between, please feel free to stop me anytime. All right, so let's substitute it. Let's substitute L2 dash of x at x equal to 3. Let's substitute those values. So this will be 1 by 20. Now if you substitute 3 here, it's going to be 2 minus 1 minus 5, plus this is going to be 3 minus 1 minus 5. Okay, now this is going to be 3, 2 minus 5. This is going to be 3, 2 minus 1. Okay, 1 divided by 20, this is positive, this is 10, plus this is also positive 15, plus 3 to the 6, 6 5s are 30, but this is negative, minus 30. Is it correct? How can I get 5? Okay, sorry. So 3 minus 7 is -4. So this will also be -4. This will also be -4. Yeah, so so please check my math. I can make mistakes. So this is going to be 8. This is going to be 12. And this is going to be -24, I guess. minus 24, and this is going to be minus 6. Alright, so this is minus 30, plus 12 plus 8 is minus 10, minus 10 by 20 is minus half. So this is minus 10 by 20, it's minus half. Okay, this is your L2 coefficient. So we have two more to go. Now L3 of x is x minus x naught, x minus x1, x minus x2, x minus x4 divided by x3 minus x naught, x3 minus x1, x3 minus x2, and x3 minus x4. So now again let's substitute the values x. So first will be simply x and x minus 1, x minus 2, x minus 7 divided by 1, 2 and 4, right? This is going to be 4. 4 minus 1 is 3. 4 minus 2 is 2. 4 minus 7 is minus 3. Okay. How much is this? 9. 3 into 3 into 2 into 4 is 72. Is it right? 4 minus 3 is minus 3. Yeah, 72. Minus 1 divided by 72 into x, x minus 1, x minus 2, x minus 7. Now L3 dash of x, let's differentiate it. That is going to be x minus 1, x minus 2, x minus 7 plus x, x minus 1, sorry, x minus 2, x minus 7 plus x, x minus 1, x minus 7 plus x, x minus 1, x minus 2. Now we need to substitute the value of x at x equal to 3. It is minus of 72. 3 minus 1 is 2. 3 minus 2 is 1. 3 minus 4 is minus 4 plus 3 1 minus 4 plus 3 2 minus 4 plus 3 2 1. This is minus 8. This is minus 12. This is minus 24. This is plus 6. Okay, there's a mix you see here. Minus 8, minus 12, minus 24, plus 6, minus 38. So this is going to be plus 38. Is it right? Yeah, plus 38 by 72. Alright, this is your L3. So the final one is L4. X minus x naught, x minus x1, x minus x2, x minus x3 divided by x4 minus x naught, x4 minus x1, x4 minus x2, x4 minus x3. Okay. This is x, x minus 1, x minus 2, x minus 4. Denominator is going to be 7. So 7, 6, 5, 3. 7 minus 4 is 3. Alright, this is going to be 7, 6, 5, 3. 630 is 1 divided by 630 into x, x minus 1, x minus 2, and x minus 4. Now let's differentiate this L4 dash of x, that is going to be 1 divided by 630, the same logic. X minus 1, x minus 2, x minus 4 plus x minus 2, x minus 4 plus x minus 1, x minus 4 plus x minus 1, x minus 2. All right. If you want to substitute x equal to 3, what will happen? 3 minus 2 is 2, 1 minus 1 plus 3, 1 minus 1 plus 3, 2 minus 1 plus 3, 2, 1. All right, we are almost there. This is minus 2, this is minus 3, this is minus 6, this is plus 6. So this is minus 5 by 630. How much is 630 divided by 5 is 126. Okay, this is minus 1 divided by 126. Now let's assemble. So p dash of x, it's going to be L1 dash of x at x equal to 3. It's going to be L1 dash of x, or I can just simply write L1 of 3, f of x1, L2 dash of 3 at f of x2 plus L3 dash of 3 into f of x3 plus L4 dash of 3 f of x4. Oh, there's L0, I missed it. Okay, I will write it separately. L naught of 3 f of x naught. Alright, so we found everything. Let's just substitute it. L naught dash is what did we found? 1 divided by 23. 1 divided by 23 into f of x1, which is 4, and then this is minus 1 divided by 18 into 7, and L2 dash is, how much is it? Minus half x2 is, f of x2 is 11, and then L3 dash is plus 38 by 72 into f of x3 is 15, and plus, is it plus or minus? Minus 1 by 126 into what is the final value? 21. Damodaran, I couldn't hear you. If you have any questions, do you have any questions? For some reason, I couldn't hear you properly. Maybe you can change your microphone, or maybe you can type your question in the chat. Anyway, um, while Damodaran types, maybe we can finish this problem. So if I made any mistakes, please let me know in the calculation. So how much is this coming out to be? So 4 by 23 minus 7 by 18 minus 11 by 2 plus 38 into 15 by 72 minus 21 by 126. So I am getting something like 2.0 2.035. Okay, so basically this is f dash of 0.3 is almost near to 0.35. So why did we write this is because we have approximated using a polynomial and then we differentiated it. So it may not be exact. So it might be the approximate solution is 2.035. Okay. So this is how you solve this problem. So you need to find Lagrange coefficients and its derivatives, substitute in the polynomial, you will end up getting the derivative. All right. I hope there are no questions, should be fairly straightforward. So we will move on to the second question that I have. So the second question revolves around this. So it says the speed of car is recorded for 1.5 minutes. Okay, and this is the speed of car recorded, and compute after how much time from the start the acceleration of car will be 0. So they are telling from start, if you see, the acceleration is going to vary. At one point the acceleration will become 0. They are telling it has become 0. So at one point we were asked to find what is that time. So somewhere over, this is the speed they have given, but the acceleration is becoming 0 at one of this time. Okay, one of this time or somewhere between these times. So we were asked to find that time, and we were asked to use Newton's forward difference formula, and we all know what is acceleration. Acceleration is a is speed du by dt, right? So rate of change of velocity is the acceleration. So by looking at this table, you can find something from here. So you can see the speed keeps on increasing. So if speed increases, acceleration is positive. If the speed decreases, it's deceleration. So acceleration will be negative. So that we all know. So in this case, what you see, it started at 1 and it keeps on decreasing to 0.649. So which means it is decelerating, which means du by dt is negative. Uh, it at this point, at this point, at this point, again at this point, it's a negative. Now, from here, if you see, there is an increase in speed to 0.6 to zero point 0.7. There is an increase in speed, and then it increases to, it continues to increase, which means the speed is decreasing and then increasing. Okay. Now, somewhere, let's say if I want to plot it, so with respect to time, let's say I'm plotting velocity. um, it comes down, it starts at 1 and then it comes down like this and then it goes like this, let's say. Okay, this is your end time, somewhere this is 1.5 seconds, oh sorry, minutes, 1.5 minutes. So the acceleration, if you plot, this is velocity, which means this is, okay, sorry. So this is velocity. Let's say if you plot an acceleration um, in the same axis. So it is going to start from negative, so that we know. It is going to start from negative, and after 1 second it is keep on increasing, or after 0.75 it is keep on increasing. So it is going to be in positive direction. So somewhere between uh, at least till zero point 0.5 we know. Okay, so then let's try to mark this is this is 0.75. Okay, so from 0.75 you keep on increasing, and till zero point 0.5, let's say this is zero point 0.5, it keeps on decreasing. So acceleration is going to be something like this. Okay, so somewhere between this value, somewhere between zero point 0.5, 0.75, in this value, it is crossing the uh, 0. Okay, so this is acceleration curve. Okay, so somewhere between uh, here, the acceleration, it is crossing this time axis, which means it's becoming positive. So somewhere at what point you are getting a to be 0 is what you need to find out, and that point will correspond to du by dt to be 0. Okay, so basically what we were asked to find is we need to differentiate this, we need to find du by dt, equate that to 0, and find time. Okay, that's the thing. So but they have asked it in a more physical way. That's the thing. So the understanding why we need this is, we will know this. So I mean, we will use this understanding, because we are using forward difference. We need to find what should be your x naught, x p and h, right? So while doing such an exercise, you need to have some understanding of how a is varying. You cannot randomly choose x naught. If you remember, for the forward difference, your p should lie between I guess minus 1 to 0, right? So you need to select a x naught in such a way that p is lies between minus 1 to 0. In this case, what will be the x naught that you will choose depends upon uh, you know that will tell you, that will give you the right answer. Okay, so we'll come back to this explanation again, but I hope you understand the curves, how it is varying. So this velocity is just whatever it has given. I've just plotted it. For acceleration, based on its decrease and increase, I have just made a. That's why I didn't fill this place. It can cross here. It can cross here. We don't know where it exactly is crossing, so that's why I kept it open. So here somewhere it is going to cross. That we know. Yeah, that's the understanding you should have. Now we want to find out, so we have to use Newton's forward difference formula. If you want to use Newton forward difference, what you need to do, you need to construct a forward difference table. Let's quickly construct that. You have t, you have u. This is 0, 0.25, 0.5, 0.75, 1, 1.25, and 1.5. This is 1, 0.784, 0.649, 0.617, 0.718, 0.990, 1.482. Okay, now you need to find del u. Del u is going to be 0.784. This is going to be negative minus 0.216. This is 0.649 minus 0.784 minus 0.135, 0.617 minus 649, 0.032, 0.718 minus 0.617, 0.101, 0.718 minus 0.617, 0.99 minus 0.178, 0.272, 1.482 minus 0.492. So in here also you can see that this delta U is negative till zero point 0.5, and from 0.75 it is positive. Okay, so that's also an indication that from here to here something is changing. Okay. All right, so let's do del square U minus 0.135 plus 0.216, 0.081. Do I have this already calculated? Yeah, so this is 0.103, this is 0.133, this is 0.171, 0.220, and del cube U is 0.022, 0.03, 0.038, 0.049. Del 4U, this is 0.008, this is also 0.008, this is 0.011. Okay, let's just keep going. We try to put it in the next. Okay. Del 5U, this is 0, this is 0.003. Del 6U, this is minus 0.003. Okay, this is your forward difference table. I understand that this is not in a straight line, but I hope you guys can understand. It is supposed to be in a straight line, but all right. Now we were asked to do Newton's forward difference, right? Newton's forward difference. So what is Newton's forward difference? So Yp is y naught plus, let's look at the class notes. P delta y naught plus, I think, p minus 1, right? P into p minus 1 by 2 factorial delta square y naught plus p minus 1 p minus 2 by 3 factorial delta cube y naught plus p minus 1 p minus 2 p minus 3 by 4 factorial delta 4 y naught. How many are there? Delta 6 is there. So, oh, okay, so y here is u. Okay, maybe should I write it in u? It's fine. I think you guys can understand. Okay, you can just keep writing this like this. But what you need is dy by dx. Dy by dx. That is going to be so you might think that where is x here, right? So let's write that down. First, we need to know what is p. P is x minus x naught divided by h. What we are looking for is here we want to know what is the x. X here is t. Okay, so x is t and y is u. Okay, we want to know at what t the y is becoming 0. So we know y, but we don't know t, which means we know y, but we don't know x. So if you substitute it here, this p is a function of x. Basically, this p is a function of x. So let's say if you differentiate it, dy by dx equal to this first term will go away, second term will just become so 1 by h, you can write it outside, and x minus x naught into delta y naught will be there. That will be simply delta y naught. Okay, and plus you have p into p minus 1, that is going to be okay. Yeah, professor has already did this and he gave this notation, right? So let's just use that. P 2p minus 1 by 2 delta square y naught plus 3p square minus 6p plus 2 divided by 6, I guess. Yeah, 6 delta cube y naught, plus you can keep on adding it. So I think it will go till delta 6 y naught. Okay, so you just need to express it in this as a polynomial and differentiate it, and you can write it. That is the way. But for this problem, um, to complete it, I'm going to stop at del cube y. Okay, I will just show you. But in general, you have to go till del 6y. The reason is they have given till del 6y, so you cannot stop somewhere here. But today, just to show you how this is done, I will just stop it here. Okay, maybe if time permits, do we will do the other terms also. So now, uh, um, what we need to find out is we need to know what is p. Since we don't know x, we don't know p. But we know h. What is h? H is 0.25. For every 0.25 you are getting this. By the way, this is an equally spaced data point, so that's why we will be able to do Newton's forward difference. So this is 0.25. So this is known. Now the other thing is what is x naught, right? And what is p? Or in this case, we know dy by dx. We need dy by dx to be 0, correct? Which means du by dt, which is 0. So which means we know this part, we know h, we know delta y's. Or if you choose x naught, we will know these, and it will be only unknown will be just p. And since this is an equation with one unknown, you can easily find p. You can easily find the root of this equation to find p. And once you find p, you substitute in this relation to find x, and that x is the place where acceleration crosses from negative to positive, or in that is the place where acceleration is 0. Okay, so that is the idea. Now we need to choose x naught. That's why we analyzed it before here. We need to choose an x naught. So x naught, since it's a forward difference, we can either choose you can either choose 0.5 or 0.75, but since we are going to use forward difference, we will use 0.75. Then only we'll be able to uh, you know your p will lie between -1 to. So what we said is the acceleration is going to be uh, 0 somewhere here, right? In between 0.5 to 0.75, we don't know where exactly is. But if you use forward difference, then your p lies between -1 to 0. Okay, if you choose 0.75. But if you choose 0.5, your p will lie from 0 to 1. So in that case, you need to use backward difference. So that's why here we are going to take x naught to be 0.75. Okay, so you will see that if it is not clear right now, while finding the value of p, you will be able to see that clearly. So here x naught, let's say if you take 0.75, you will know delta y, delta square y, and delta square y naught. Let's substitute it. So So this will make P to be -1 less than P less than 0. Okay, because we know from 0.5 to 0.75 there is some change happening. Okay, later we'll see it now. This is going to be 1 divided by 0.25. Delta y naught is 0.75. This one, this one, this, and this. Okay, let's substitute it. Y naught is 0.617 plus 2p minus 1 by 2 into del square y naught is 0. Oh, it's sorry. This is delta y naught, right? So delta y naught is 0.101. 0.101. This is del square y naught is 0.171. 0.171 divided by 2 plus 3p square minus 6p plus 2 into delta cube is 0.049. 0.049 divided by 6. Okay, so in this case, fortunately there is no del power 4, del power 5, del power 6. So if let's say if you are using let's say you were asked to find acceleration where it is not 0 but it is decelerating, so let's say some -1 or something, then it might lie somewhere here. At that case what you have is you have till del power 5. So in that case you need to have additional terms. In this case it's going to stop here, so there is no problem. I mean problem in the sense it has simplified our job. That's the thing. All right, let's simplify this further. So this is 0.171 divided by 2 is 0.25, 0.101 plus 2p minus 1, 0.0855 plus 3p square minus 6p plus 2 into 0.049 divided by 6, 0.00817. Okay, 0.25 0.101 plus 2 into 0.0855. Oh, nice. This is 0.171p minus 0.0855 plus 0.00817 into 3, 0.0245 p square minus 6 into 0.00817. So if you guys have the final polynomial, please let me know. 0.049p plus 0.00817 into 0.0163. equal to 0.25. Mm, so 0.101 minus 0.0855 minus or plus 0.01634, 0.03184, and then 0.171 minus 0.049, which is plus 0.122p plus 0.0245 p square. Okay. If you simplify this, what will happen? 0.0245 divided by 0.25, 0.098 p square. So this is 0.98 p square. Oh, 0 means you can just remove this. It's not a big deal. So this is going to be 0.0245 p square plus 0.122p plus 0.03184 equal to 0. So you can divide by 0.122 divided by 0.0245. So this is p square plus 4.9796p plus 0.03184 divided by 0.0245, 1.2996 equal to 0. Okay. Now what can we do to find the p? So there is this minus b plus or minus square root of b square minus 4ac divided by 2a, right? We can do that. So that is going to be minus 4.9796 plus square root of b square is 4.9796 square minus 4 into 1.2996 divided by 2. Let's see if I did the arithmetics right. 4.9796 square minus, let's see, 4.426. This is minus 4.9796 plus minus 4.42696 divided by 2. So minus 4.9796, wait, 4.42696 minus 4.9796 divided by 2. So one of the p is minus 0.2763. Okay, the other p is it is going to be negative. It's going to be more negative. So it's been 42696 plus 4.9796 divided by 2. So that is going to be 4.074. Okay. So now we have two set of p's. So but you know about p, right? What is the special about p? P should be less than 1, right? So especially for this, so p is p should be minus 1 less than or equal to p less than or equal to 0. So which means this solution is invalid. So which means your p is going to be minus 0.2763. Okay. I hope you guys are following me. I just did mathematics, some arithmetics. So basically what I did is I substituted it. I got a p in terms of as a polynomial and then just tried to find the root. and I'm just going to choose only the root which makes sense in this scenario, which is p equal to minus 2763, and this is equal to x minus x naught by h. So what you need is x is equal to x naught minus ph, or x naught plus ph, correct? This is going to be x naught is 0.75 into minus 0.2763 into this is p and this is h is 0.25. How much is this? 0.2763 into 0.25, 0.69, 0.75 minus this. So x is 0.6809, which is basically time, t equal to 0.6809 minutes. So at this place, your du by dt is 0. Sorry, du by dt is 0, correct. Acceleration is 0. So this is what has been asked. We were asked. Fine. Okay. Is that clear? So basically it is lying between, as we guessed before, it is lying between 0.5 to 0.75. It is going from here to here, because our delta u also we found it is going from minus to positive, which means somewhere in between it's going to be 0. Any questions? Okay, I'm guessing there are no questions. Let's move forward with the final question that we have here. So the third question is, we are going to use Bessel interpolation formula, and again we are going to find the derivative dy by dx. The following x and y data are used. So basically we are going to implement Bessel, we are going to use Bessel formula to find dy by dx. In this case, we need to find it exactly at 7.51, okay, whose function value is given, but we need to find its derivative at this place. All right. So for Bessel interpolation formula, if you remember, again we write the forward difference table, and then we'll write the Bessel's uh, formula written in terms of forward differences, and we substitute those values and we get the result, right? So similarly, the first step is to write the forward difference table, which is x y is 7.48, 7.49, 7.5, 7.51, 7.52, 7.53, and 7.54. This is 0.713, 0.182, sorry, 0.196, 0.2, 0.207, 0.211, and 0.216. Now the forward differences are 0.182 minus 0.73 is like 0.09, 0.009. This is 0.14, 0.14. This is 0.004. This is 0.007. This is 0. Again 004. This is, sorry, this is 0.005. Now del square y. What is this? 0.005 minus 0.01. Correct? Yeah. This is 0.003. This is minus 0.003. This is minus 0. No, no, 0.001. Now del 3y is this minus this, so it's going to be minus 0.015. This minus this, so this becomes positive 0.013. This minus this, so it's going to be negative 0.003. This minus this, it's going to be positive 0.004. And then del power 4y. This is 0.028. This is minus 0.019. This one is 0.01. Then del 5y. This minus this is going to be more negative 0.047. This minus this, it's going to be positive 0.009. This is positive. So this minus this is going to be 29. And del power 6y, it is 0.076. Okay, positive. So this is your forward difference table. Now let's write the Bessel's formula. What is the Bessel's formula? Is it Bessel? Yeah, Bessel's formula. Just give me a minute. So we know the Bessel's formula. It's going to be, let me write down the formula of y first, then we will do dy by dp. So y is yp is y naught plus y1 by 2 plus p minus half delta y naught plus p into p minus 1 by 2 factorial delta minus 1 plus delta 2y0 divided by 2 plus p minus half p minus 1 divided by 3 factorial delta cube y minus 1. Similarly, you can keep on writing like this. But what we need is dy by dx. Dy by dx. And also, so what we need to find it at 7.51. So dy by dx. So let's look at the class what professor has wrote. Bessel formula. This is the one, right? Oh, sorry. This is the one. So we are going to do the same thing. Here we can write it as 1 by h so delta y naught minus 1 by 2 minus 2p minus 1 by 2 into mu delta square y naught. Wait. So this delta, right? Delta y half plus 2p minus 2y into mu delta square y half plus 6p square minus 6p plus 1 divided by 12 into delta cube y half plus 2p cube. I think professor didn't write that. Okay, he wrote it. Minus 3p square minus p plus 1 divided by 12. So basically, what we need to do is we will write all the other terms and then we'll differentiate this term. That will give you this polynomial. Okay. So it's not something new. Mu del power 4 y half. Correct. And then you can keep on doing this. Now for this problem, x is equal to x naught equal to 7.51. So that is where we want. So this is where we want dy by dx. Okay, at this place. So your y, delta square y, and delta power 4y. Actually, this is not forward difference, right? This is not forward difference. So we will come to that. But what I want to tell is x naught is 0.71 and your xp is also 0.71 and h is 0, sorry, 7.51 and h is 0.01, I guess. Yeah. So if this is the case, your p is going to be xp minus x naught by h, which is 0. Okay. Which means these terms can be simplified. So these terms can be simplified. These terms will go away. Okay. So if you simplify that and write the formula, it is going to look something like this: dy by dx is equal to, and whenever you have mu, you do average, right? So in this case, you have delta square having an average. So this you will select. For delta square, you need to do an average of this and this. This is a forward difference. And for delta 3, you no need to do an average. So you will take this. And for delta power 4, you need to again do an average. So you will take this and this. And for delta power 5, you will use this. And for delta power 6, you have to use this and the another one. But that is not existing. So maybe we can stop here. Okay. We can either stop here, we can also stop here, but we don't know the previous value, so it's better not to go there. We will stop here. All right, so till fifth, del power 5, why not we need to write. So this is going to be, so at x equal to x naught, it's going to be 1 divided by h delta y naught minus, so this thing is p is 0, so it's minus 1 by 4 into this will be again half. So this will be, sorry, minus 1 by 2. This will be again half. So this will be minus 1 by 4 minus into minus plus 1 by 4. Okay, wait a minute. I think this has to be, this is wrong, this is to be plus, right? Is it right? Yeah. Okay, everything is plus. Yeah, this has to be plus. So in this case, it will be, this is 0, so this is minus 1 by 2 into mu as another 1 by 2, so it will be minus 1 by 4. So I'm just going to write this as minus 1 by 4. Mu is delta y naught and delta y minus 1, and then plus 6p, all these things will go away, and then there will be just 1 by 12 left, 1 by 12, and delta 3, sorry, this is delta 3 y minus 1, and then the fourth term will have Fourth term, all these will go away. This will be 1 by 12, and there is a mu which has half. So we can write this as minus 1 by 24. Is it minus or plus? So it's plus 1 by 24 uh, into delta 4 y minus 1 and y minus 2. And the fifth one is going to be minus 1 by 20 delta 4 5 y minus 2. Okay, we will stop here. Actually, you can write it like this, but we will stop here because we do not have any of variables above. Now let's substitute it. H is 0.01, delta y naught is 0.07007 minus 1 by 4 into y naught and y minus 1, which is minus 0.03 and plus 0.03. I think those two will cancel by 0.003 plus 0.003 and plus 1 by 12 into y minus 1, sorry, delta cube y minus 1, right? Yeah, delta cube y minus 1 is minus 0.006 plus 1 divided by 24 into delta power 4 y minus 1 and y minus 2, which is 0.01 minus 0.019, 0.01 minus 0.019 minus 1 divided by 20 into del phi is 0.0029, 0.0029. Okay, let's simplify this. 0.01, this will go away, so you will have 0.007, 0.006 divided by 12 is minus 5 into 10 power minus 4, which is 0.0005. Correct. And 0.01 minus 0.019 divided by 24, which is minus 0.0000375, and 0.0029 divided by 120, which is minus 2.4167 into 10 power minus 5. Okay, so now let's add them together. 0.007 minus 0.0005 minus 0.000375 minus 2.4167 into 10 power minus 5. So this comes out to be around 6.1 into 10 power, you can just simply write it as 0.0061 divided by 0.01. 0.0061 divided by 0.01. This is equal to 0.61. So at dy by dx at x equal to 7.51 is 0.61. Okay. Yep. So just you need to write you need to make a forward difference table and then apply Bessel's formula, and then straightforward simplification will give you the final answer. Okay. All right. Any questions? If we today we saw like three problems. One was on Lagrange interpolation. The other one was in Newton's forward difference. The other one is on Bessel's interpolation formula. Okay. If you have any questions, please let me know. This is what I have today. So next week we will see numerical integration, some problems on numerical integration, and I think the last week is about uh, ODEs. How do you solve ordinary differential equations? And that is where we stop this course. It's an 8-week course, and there will be one class on uh, revision. So we will just go through whatever we studied for in the entire course. Okay, that will, I think the exact time and date you will receive an email from the NPTEL officially. Okay, that will be after our week 8 problem solving session. All right. If you have any questions, please let me know. If not, thanks for joining. I think we have like 3, 4 people today. Thanks for joining, and we will meet next week. All right, guys.